Okay, let's go ahead and do an example. Okay, we will let f equal to, we're going to use the same vector field as before, so we have cosine of xy, and we have sine of x squared y, actually kind of a complicated vector field. We have c of t, which is as before. We'll write the parameterized version, which is 4 cosine of t and 2 sine of t, or we'll write it in Cartesian, x squared plus 4y squared equals 16. It is the ellipse centered at the origin, major focal radius 4, minor focal radius 2. So we're going to go ahead and calculate both integrals. We're going to calculate the line integral. We're going to calculate the double integral. So let me go ahead and start this over here. Let me just draw out our particular region so we remember what we're talking about here. So we have this ellipse. This is minus 4, this is 4, this is 2, this is minus 2. So we're going to go ahead and calculate the line integral. We're going to integrate in the counterclockwise direction, keeping the region to our left, and then we'll go ahead and calculate the double integral. Okay, so we want to do our first one. So we want to calculate the integral over the boundary of f of c dotted with n dt. Well, f of c, that's going to equal, let me do this a little bit below so that I have as much room as possible. So let me see, I've got, so the f of c part, I'm just going to put in c into f. It's going to equal cosine of 8 cosine t sine t, and I'm going to get sine of 32 cosine squared t sine t. And again, I hope that you will confirm this for me, and if I make a mistake, shouldn't be a problem. Just make sure, go with what you think it is, if in fact I've made a mistake, and just put it into your math software and you'll get the particular answer. Okay, well, we need c prime of t, right? F of c, we need c prime of t so that we can form n and then take the dot product. So c prime of t, that's equal to minus 4 sine t and 2 cosine t, right? So now we form n. Well, n of t, we switch these two and we negate the second. So this equals 2 cosine t, and this becomes minus 4 sine t minus minus 4 sine t, so it becomes 4 sine of t. So now let's go to blue. So now I have my f of c, that's this one. I have my n of t, that's this one. Now I take the dot product of those two. So f of c, that's it, that's all I'm doing. Just plugging things in. F of c dot n is equal to, it's a little long, 2 cosine t cosine of 8 cosine t sine t, excuse me, plus 4 sine of t times the sine of 32 cosine squared t sine of t. So it's a little long. I don't want to keep writing this, so I'm just going to refer to this as z. Therefore, the integral around the closed curve of f of c dot n dt, in other words, the flux of this vector field across this closed curve, is going to equal the integral from 0 to 2 pi of this z dt. When I put it into my math software, I get the number 0.5466. There we go. It's just a number. It's a negative number. Negative flux means that the vector field is actually not moving away from, it's not moving across the curve outward, it's moving inward. In other words, it's this way. The vector field is actually contracting, going, fluid is flowing into the region. Fluid is not flowing out of the region. That's what this is telling me for this particular vector field. If this particular vector field happened to represent fluid flow across this ellipse. Okay, so now let's go ahead and do the double integral just to make sure that you do actually end up getting the same number and that Green's theorem is correct. It is, but it's good practice, you know, because we need to actually solve the double integral. So now the double integral. So now the double integral. And I really like this blue ink. It's nice. The double integral. Okay, so we want to solve a divergence of f dy dx. Okay, well, we calculated the divergence of f. So let's just recall what that was. And if we don't recall, let's just go ahead and do it again. We have our vector field. It's minus y times the sine of xy plus x squared times the cosine of x squared y. Okay, so now let's go ahead and put it in. So the double integral over a of the divergence of f dy dx. All right, now our x is going from -4 to +4. -4 to +4. Our y is moving from -16 minus x squared under the radical divided by 2 all the way up to radical 16 minus x squared over 2, the positive. It's the lower, that's the upper. That's what y is doing. Our divergence is minus y times the sine of xy plus x squared times the cosine of x squared y dy dx. When I go ahead and put this into my math software, guess what number I get? 0.5466. Negative 0.5466. So this confirms that the flux integral is equal to the divergence integral. It confirms the fact that this particular vector field is actually, it has a negative divergence. It's contracting. Fluid is flowing. There's a net flow. This is a net. Remember, we're integrating. At a different point, at different points inside there, you might have a positive divergence, but when you add up everything, the net flow is into the region. Okay, so let's go ahead and write this out. So since negative 0.5466 is negative, this means that there is a net flow of the vector field into the region. Into the region. In other words, if we have our the vector field as a whole is contracting. Okay, now in the previous lesson, we found that the curl of this particular vector field, the curl of f, was equal to 0. So this particular vector field is contracting into the region, but it's not rotating left or right. This is really, really powerful that we can make this kind of a statement about a vector field given a particular closed region. Really, really extraordinary. Okay, thank you for joining us here at Educator.com for Divergence and Curl. We'll see you next time. Bye-bye.